Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing, testing. Testing, testing. Okay, I think it's testing good. Volume looks good. YouTube looking good. All right. Pretty much ready to go. Just got to get X. Waiting on X. All right. Pretty much ready to go. This is a little weight and biases container that I got when I worked there. All right, now we just need to wait on X. All right, it should be, seems like it should be good. How's it going, Josh Phillips? How's it going, Ed? What? We got no more coffee. Uh-oh. Uh-oh. That's not good. Whatever, we'll have to improvise. How's it going, John? And I think we're live on X, so let's go ahead and get this thing started. Alrighty, so welcome to another Hoopo stream. Today we got kind of a mixed bag of LoRa papers to read through. So the official name of the stream is LCM Lora, S-LoRA, and then LoRAX or LoRAX. And I'm just going to cut to the chase. The unfortunate thing is that when I was browsing through these papers, I thought all of these were a little bit more related than they really are. So LCM Lora is a little bit different than S-LoRA and LoRAX. S-LoRA and LoRAX are a little bit more similar. They're related to kind of like performance and getting multiple LoRas to run. But LCM Lora is kind of like its own little standalone thing. So I think the way that I'm going to do it is I'm going to just quickly review LCM Lora, and then we'll go and we'll spend the majority of the time looking at S-LoRA and LoRAX. How's it going, Finkborn? And how's it going, The High Nugan? So, how's it going, Din Nugan? Am I pronouncing that right? I have no idea how to pronounce that. Okay, so I know most of you probably already know what this is, but bear with me because I want to make this content approachable to people that don't necessarily know everything. And what exactly is a LoRa? So a LoRa is a low rank, so L-O for low, and then R for rank, and then A for adapter. So what a LoRa does is it's basically an additional matrix in addition to the weights that you can train such that you can adapt the behavior of an already existing neural network. So it's not limited to any type of neural network or even any kind of modality, right? You could have a LoRa that's for a diffusion model for images, and you can also have a LoRa that is for a language model that consumes text. So LoRa is a generic technique for fine-tuning or adapting the behavior of a neural network. And basically the way that it works is it uses a low-rank matrix or a pair of these. So basically you have a A matrix and a B matrix. Here, this is the documentation for performance efficient fine-tuning or something like that. It's a Hugging Face kind of framework or set of tools that you can use for training LoRa's. But yeah, basically LoRa's, these pairs of matrices A's and B's, because they're lower rank, that means they have a less total amount of numbers, which means that you can basically, rather than fine-tuning the original model, you can fine-tune these matrices only, and it's a lot cheaper, it's a lot faster, and then you can also kind of hot swap them in, right? So you can basically take your original pre-trained model, add one LoRa, take out a different LoRa, put a new LoRa on, so you can kind of swap them in, and they're very composable, and it's a nice little clever trick that kind of everyone's in love with in the fine-tuning community and open source community. So hope that was a nice little quick summary of LoRa's. If you're still confused about what a LoRa is, I would recommend reading this or maybe watching some of the other streams where we've gone over LoRa's. So with that, let's go into the first paper here. This is LCM Lora, a universal stable diffusion acceleration module. So stable diffusion is a diffusion model created by a company called Stability AI that is used for text to image. So text to image, as in you give it a little piece of text, and then it uses that little piece of text to condition a diffusion model, which slowly removes noise from basically white noise, and then it creates the image that you want that is going to be kind of related to that text. So LCM Lora is kind of based on actually, why don't we just read the abstract, and then we'll go and kind of explain what's going on here. So this is 9th November 2023. 9th November 2023, so relatively recent paper, and it's coming from a bunch of people at Tsinghua University and Hugging Face as well. So Hugging Face has some researchers in-house that work on this kind of stuff. So latent consistency models, LCMs, have achieved impressive performance in accelerating text-to-image generative tasks. So latent here has to do with the fact that most of these diffusion models don't operate in pixel space. They don't operate or remove noise in the actual image space. They're removing noise in a latent space, which is, you can kind of think of it like a more compressed, abstract version of the image. The exact consistency models, we have the paper pulled up for it, but we will go to it in a second here. Producing high-quality images with minimal inference steps. And this part is key here, right? Because the way that diffusion models work is they require multiple inference steps. Inference steps is basically like one feed forward through the GPU, right? So every time you evaluate something, you're performing inference. That's when you're actually using the neural network. So here, this is the actual consistency models paper. You can see it's a little bit older now. It's 2 March 2023. I think we actually did do a stream on this, so you guys can go ahead and check that out if you're interested. But basically, what I want you to look at here is this figure 1, which is starting from noise, and then at the very end here, you have this picture of a dog, right? And this shows you how in a diffusion model, you have to perform many of these inference steps, right? So going from here to here to here to here to this is 1 inference step, 2 inference step, 3 inference step, 4 inference steps. And you can see how you're trying to remove the noise from this image, or really from nothing, and you're conditioning that removal on some text. And you train this on a huge data set of basically images and text, and when you're training it, you're basically adding noise, so you're doing the opposite process. But as you can see, it doesn't do it entirely in one shot. You basically need to run this noise removal a couple times, in the order of like 10 or potentially even more times, in order to get your final image so that it's nice and clean and crispy. Okay, so that's ideally, if you want to make these diffusion models as fast as possible, you do that either in one step or as few steps as possible, right? Doing it in one step is going to be very difficult, but ideally you want something less than like 10 or 4 or something like that, right? So LCMs are distilled from pre-trained diffusion models. Okay, so what do they mean by that? So let's go back to the LCM paper here. So in the LCM paper, this is kind of a very math-heavy paper, and basically you can go kind of super deep on this, but one way to think about what a diffusion model is that it's a probability flow ordinary differential equation, ODE. And basically what is happening is you can think of basically the noise process. You have some specific type of noise that you're adding to this, and progressively adding more and more noise is basically like almost like you would I'm trying to like think of the right word that doesn't sound like too confusing, but like one way to think about it is that it's kind of like Brownian motion, right, where you have a bunch of little particles moving. So the as you kind of remove noise from this, you're not necessarily taking the most optimal path, right? So if you were to actually look at the individual values of some of the pixels here, they wouldn't go straight from the noise value down to a straight path all the way to the final pixel color of this dog, right? So like it wouldn't go straight from whatever the pixel value is here to there, right? It would basically go through a couple, maybe get a little bit darker, get a little bit lighter, get a little bit darker, get a little bit lighter, right? It's going to move in a way that's not necessarily super fast and optimal, right? And there's the additional complexity that it's not even doing that in pixel space. Remember, it's doing that in latent space, right? But what this consistency models paper showed was that, hey, maybe rather than, or not maybe rather, but what if we distilled a model that tried to be as consistent as possible between the initial kind of noise distribution and the final data distribution. So here when they say noise, think of this noise image here, right? And then when they say data, think of the picture of the dog. It's just that here they have it represented in kind of as a distribution. So this is, you can think of it like the distribution of noise, and then here's the distribution of the data, which is going to be your image distribution. So rather than having a diffusion model that kind of goes from noise to data in a bunch of steps, sample some of the pairs between that and say, okay, well, here's the image halfway through this process, and then here's the image at the end, and that should be the same ultimate path as starting from step 1 or starting from step 9 or starting from some arbitrary step. So what these consistency models are really doing is they're basically trying to distill or train a new model from an old model, where the old model is the original stable diffusion, and the new model is going to be a stable diffusion that basically tries to give you the same quality of the final image, or basically get the same final data distribution from the original noise distribution, but in less steps. So you see here how basically here you're starting from the very end and you're going to the time 0. Here you're starting at time step a little bit more towards the middle and then going all the way to 0. And then here you're starting at time step, whatever this is, t, and then going to the middle. And then the consistency model is trying to say all three of these paths should basically end up at the same place. And if you do that over and over and over again and kind of distill and just give it more and more examples of this, eventually you basically get a diffusion model that does it in less steps, right? So rather than having to take 10 steps to go from noise to data, you can basically do it in 4 steps. So consistency models are basically a trick that are leveraging the fact that the path that basically each of these little individual parts of the noise distribution take all the way to get to the data distribution is not like a straight line. It's very kind of back and forth. So therefore, we can distill a model that takes a more efficient path to the final image, right? So that's a little review of consistency models. How's it going, Liu? How's it going, Khalil? How's it going, Amelie? So, all right. So LCMs in their original kind of formulation were distilled basically entirely, right? So you're training a new model or distilling a new model from the original diffusion model. And the clever thing that they do in this paper is that rather than distilling into an entirely new diffusion model, they're going to distill it into a LoRA, right? So they're constraining the space in which you're pushing in this new type of consistency model into just a LoRA, right? So in the original consistency model, you're changing this crap here, right? You're changing the full weights of the original diffusion model. But in this paper, the LCM Lora, what you're doing is you're only pushing gradients into a little LoRA, and that means that little LoRA is going to be, I keep coming back to that tab, but I'll come back to it later. It's going to be a much, it's going to be something that you can then put onto a different Stable Diffusion, and it works completely fine, right? So you don't have to keep a big, full Stable Diffusion that has, or LCM model. You can basically just take an already existing Stable Diffusion model, apply your little LoRa, which has that kind of LCM magic in it, and then now that Stable Diffusion model will have the LCM magic in it. Okay. By applying LoRa distillation to Stable Diffusion models, including Stable Diffusion v1.5 and SDXL, we have expanded LCM scope to larger models with significantly less memory consumption, achieving superior image generation quality. We identify LoRa parameters obtained through the LCM distillation as a universal Stable Diffusion acceleration module named LCM Lora. LCM Lora can be directly plugged into various Stable Diffusion fine-tuned models or LoRas without training, right? So basically, they've taken all the LCM juice, packaged it into a little LoRa, called this LCM Lora, and then if you have your own Stable Diffusion model that has some other LoRa applied to it, you can add this LCM Lora, and it'll still be pretty much the same, except now it'll be able to do it in less steps, right? Now, rather than taking 10 steps of inference to generate your image, it'll only take maybe 2 or something like that. Compared with previous probability flow ordinary differential equation solvers such as DDIM, DPM, LCM Lora can be viewed as a plug-in neural PFODE solver that possesses strong generalization abilities. Okay, so I think the best way to motivate kind of what's going on here is with a little demo, and this is a Hugging Face space showing just how fast LCM Lora is. So, for example, let's do a frog, and you can see how, not a frog, a frog. Boom, we got a frog on a log. And you can see how fast this is. Holding an umbrella. Holding an umbrella. There we go. That is blue. Where's the blue umbrella? Blue. There we go. So you can just see how much faster this is, right? Which is pretty cool. This is still SD 1.5, which is not even the latest SD. Like, the latest Stable Diffusion is actually SDXL, this one here. But SDXL is a little bit more complicated too, because the SDXL has like this additional refiner model. So the LCM isn't going to make the refiner model faster. It'll just make the original diffusion model. But then you have to do all the other crap that SDXL has as well. What architecture does this consistency model rely on? So the specific part of the model that you're applying the LCM to is the diffusion model. So in the Stable Diffusion, there's actually a couple different models. You're going to have your unit that, or you're going to have a model that actually compresses the image into a latent. Here, it looks like you're adding and removing noise in pure image space, but usually the Stable Diffusion models, what they're doing is they're adding and removing noise in a compressed latent space. So you're doing it in the diffusion model. Seemed like this would be pretty useful for things like animation generation, where number of frames is significant. Yeah, it's a nice speed up. It's very quick, and I think that now that we've gotten to this like sub 5 seconds, sub 1 second like inference speed, it's kind of like a game changer in terms of like the actual flow that you're going to use in whatever artistic flow you're using to do stuff. Okay, so I think this figure one kind of pretty important here. Actually, wait, let's show this one here. So this figure here is showing you the result of a diffusion model at multiple steps, right? So here where it says 2-step, 4-step, 8-step, 16-step, 32-step, that's this, right? That's basically the number of steps that it takes to get to an image. So you can see that the original, ignore the kind of paper cut LoRa here, but the original diffusion model, it takes about basically 16 steps to give you something that looks good, and then it takes 32 steps to really give you that clean, crispy picture of a Pikachu that you're looking for, right? But once you add this LCM Lora, right, you can see how it gets there in way less steps, right? So now, even just in 2 steps, you have something that is kind of reasonable, right? So basically, because you now have you've trained this or distilled this thing to basically be consistent no matter where or how many steps you're using, it's now able to work at a much smaller amount of steps. Damn, I keep bouncing all over the place. I'm sorry. And same thing here. You can kind of see how like the original paper cut LoRa, whatever diffusion model here, you can see that it takes 32 steps to get to what you want, but with this LCM LoRa, it gets there much, much faster. So that's kind of how you're getting that speed there. But the other kind of cool thing about this paper is that they realize that you can actually combine this with more or other LoRas, right? So the LCM LoRa is the LoRa specifically for this latent consistency model, right? And here, the theta base, you could basically think of that like the parameters of this diffusion model, of this latent diffusion model, right? So whenever you're using a LoRa, what you have to do is you're basically you're combining the weights together, right? So if you're actually going to use a LoRa, you have to basically you can either merge the weights in, which means that you're basically doing this. So rather than saying I'm going to take my original weight matrix times the input plus my B and A matrices times the input, and that's going to be my output. So H is my output. Rather than doing that, I'm going to merge the weights together. So I'm going to say I'm going to take my original weight matrices, I'm going to add the B and A matrices, and then I'm going to multiply that W merged by X, right? So there's this concept where you can merge the LoRas into the original weight matrices. And it's not limited to just one LoRa, right? You can add more. So you could add plus BA LCM LoRa plus BA from some other LoRa. And that's basically what they're doing, right? They're saying, hey, you can combine these with some other LoRa. So if I have my LCM LoRa, and then I have in this example, they have a paper cut LoRa, so some LoRa that specifically gives you this paper cut kind of image look, you can combine them together, and the new LoRa will not only have the style of the paper cut, but it'll also have the speed of the LCM, right? So this is pretty cool, right? Because it basically means that you can add this LCM LoRa to any other LoRa paper that you've created, and then get the combination of those. And I do want to say one thing, though, is that, actually, before we do that, let's read this. Overview of LCM LoRa. By introducing LoRa into the distillation process of LCM, we significantly reduce the memory overhead of distillation, which allows us to train larger models. Here they're referring to the fact that normally when you distill a model, you're basically pushing gradients into an entire model, but by distilling into just the LoRa parameters, that's a much more efficient way to distill models. More importantly, LoRa parameters obtained through LCM LoRa training can be directly combined with any other LoRa parameters, obtaining fine-tuning on any particular style. Without any training, the model obtained by a linear combination of the acceleration vector and style vector acquires the ability to generate images of specific painting style in minimal sampling steps. Okay, so that's basically what we just saw, right? Where you can combine these LoRas together and then get kind of the benefits of both. But one word of caution that I'm going to say here is that you can't just indefinitely keep combining LoRas together, right? And here I have a loss landscape of a neural net, and basically this is a visualization of the loss, which would be in the z-axis, compared to the weights of some imaginary little neural net that has only two weights. It has the value of weight number 1, which will be this axis, and then the value of weight number 2, which will be this axis. So any point in model parameter space is basically like a little point on this landscape, right? So whenever you're adding or merging in this BA, right, this LoRa, you're shifting. You're basically taking a little step. So the behavior that you would expect for a point here is kind of the same for the behavior that you would expect for a point here, right? As long as it's kind of close. But if you start adding too many of these LoRas together, right, if the total combination, you just keep adding more and more LoRas, eventually you're going to start moving away from the original point, and you might get to somewhere where it's basically nonsense. So even though here they kind of make it seem like you can just kind of keep indefinitely chaining these LoRas together and just add 500 different LoRas together, that's not quite the case, right? And if you kept adding more and more LoRas, eventually you're going to move so far away from the point of the original base model that the performance is going to start to degrade. So that's something to caveat this. But yeah, that's basically this LCM Lora. Very cool little trick. It's not a very long paper. It's literally just 5 pages, but it's not a very complicated paper, right? All they basically did was just LCM into a LoRa and then combined it with a style LoRas, and then really it's more of a cool demo, which is great. And I think this is going to be pretty huge for people. Let's see, a llama on a boat, come on, with a frog. Where's that frog? There's no frog. With a frog in a hat. Yeah, so it's not quite like the best diffusion model, but I've also found that you have to have a space. I don't even know what this is. This is a weird llama frog. That's kind of almost disturbing. Okay. All right, but so like I said, this is just LCM Lora, but it's a little unrelated to the other 2 papers that I wanted to talk about, which is S-LoRA and then LoRAX. Okay, so we'll kind of close the chapter there, and now we're going to talk about LoRAX. Maybe a second for questions, if you guys have any questions there. I wonder why SDXL don't try rectified flow. Maybe they didn't read the rectified flow paper. Probably. There's so many different techniques nowadays in papers that it's like people don't try everything. You know, you got a limited attention budget just from a human attention standpoint. So like if you're a guy, somebody working at Hugging Face, like you're not going to be able to do everything. So you just got to kind of pick the things that you want. All right. So LoRa Exchange, or LoRAX, is not even a paper. It's basically a talk, I guess, or something like that. There's a YouTube video for it, but there's like this company, and there's a YouTube video for this, but I don't necessarily even recommend the YouTube video because it's very promotional. They just keep trying to sell you their weird startup. But I think they pose an interesting problem, which I think sets up the S-LoRA paper nicely, right? And let's say that you're a startup, right? Or you're a company that is serving models, right? So serving fine-tuned models. What does that mean? It means that if you think about the terminology of like the web, you have clients, which are going to be your customers, and then you have the servers, which are going to be you providing something to your customers, right? You're providing, in this case, intelligence to your client, which is the user, right? So, and the way that intelligence is going to be provided is via different fine-tuned models, right? So if you're serving models for a set of customers, those customers are going to have different desires, and the different desires, you're not going to be able to serve the same exact model for all of them, right? You're going to have a different fine-tuned model for different customers, for different use cases. So how do you do that in a way that's kind of efficient, right? So here what they say, and here this little box here basically tells you that this is one computer, right? So one thing you could do is you could say, okay, well, I'm going to load this model, which has this LoRa, right, is this fine-tuned model. So this is the model, and then the little blue part is the LoRa. So here you can see that the LoRa is only on specific parts of the model. So I'm going to have one computer that has this model with this LoRa loaded, and then I'm going to have a different computer that has this model and this LoRa loaded, and then I have a third computer with this model and this LoRa loaded. And you can see how if you start getting way too many models, it's going to start getting very complicated very quickly, right? You don't want to have 100 cloud GPUs sitting there, each with a different LoRa, just in case each of your different customers wants to serve it, right? Ideally, you want to have basically one computer that can serve every single type of LoRa, and then it can do that kind of dynamically, right? So dynamic adapter loading. Adapter is just a LoRa, right? So basically, you want to have the original model, and in this LoRAX, they're basically talking about Llama 27B. So they have different LoRa's for different types of Llama 27Bs, right, which is our language models. But they want to do that all with kind of one. They want to have one Llama 2 pre-trained weights, and then they want to have different LoRa's that can be kind of hot swapped in depending on which user is asking for different things, right? So that's what LoRAX is all about. So blah blah blah. Here they talk about LoRa's. Okay, here we go. Dynamic adapter loading. Unlike conventional serving infrastructure that preloads all the model weights, LoRaX only loads the pre-trained LLM weights and then dynamically loads each set of fine-tuned LoRa adapters just in at runtime. To avoid blocking ongoing requests, the LoRaX system maintains an individual request queue per fine-tuned adapter. While the new fine-tuned model adapter weights are being dynamically loaded, all of its associated requests will wait in queue while the other requests are proceed as usual. In practice, we've observed that the overhead of dynamically loading a new adapter to be on the order of 200 milliseconds, much less than the typical text generation response time, making it possible to start interactively evaluating your fine-tuned models immediately after training completes. Okay, whatever. They're a little bit flowery, which is why I'm not necessarily going to spend too much more time on this, but I thought it was a great way to kind of think about how are you going to be serving a fine-tuned model when you have a bunch of different LoRas and you want to do that in a compute efficient way, right? So kind of a cool thing to think about. Okay, and that finally takes us to the meat of today's stream, which is going to be this paper. This is S-LoRA serving thousands of concurrent LoRa adapters. So thousands of LoRa adapters. And concurrent just means basically at the same time. So you're going to be serving all of these different possible LoRa's, all with just basically one node, right? This is 7th November 2023, so relatively recent paper. And let's go ahead and get started. Let's read this abstract. The pre-trained then fine-tuned paradigm is commonly adopted in the deployment of large language models. And not just large language models, right? That's the same thing that people are doing with these diffusion models, right? Where you have one pre-trained latent diffusion model, and then you have different LoRa's for different styles, and now we have a LoRa for making it faster via this consistency model kind of trick. Low-rank adaptation, a parameter-efficient fine-tuning method. The parameter efficiency here comes from the fact that LoRa's are much smaller in rank, right? So the total amount of numbers here is less than the total amount of numbers here, right? Because a matrix that is D by D is a lot smaller than two matrices that are D by R and then R by D, right? Just the way that multiplication works out, these low-rank matrices are just less numbers than that. Often employed to adapt a base model, so that's kind of where the word adapter comes from, right? You're adapting this pre-trained base model to a multitude of tasks, resulting in a substantial collection of LoRa adapters derived from one base model. We observe that this paradigm presents significant opportunities for batched inference during serving, right? So you're serving this model, and you don't want to basically serve requests one at a time. You want to batch them together, right? So you're paying for that GPU time. You as the server are paying for that time in the cloud. So you want things to be fast, and you want them to be cheap. And the way to make them fast is batch them together. But you can't just batch everything together, right? They have to be related. They have to be using the same LoRa, and that's kind of what they're going to be answering in this paper. To capitalize on these opportunities, we present S-LoRA, a system designed for scalable serving of many LoRa adapters. S-LoRA stores all adapters in the main memory and fetches the adapters used by the currently running queries to the GPU memory. Okay, so they're going to be playing tricks, right? And this is just kind of the name of the game when it comes to like performance and inference and like doing things efficiently and batching, is that like you basically have to play this memory shuffling game, right? Like ultimately, a computer is basically a series of memory caches that are increasingly further and closer from the actual processor that's actually doing the calculation, right? So inside the GPU, there is memory that is directly in the GPU, right? There is memory in the GPU known as the GPU memory, and that memory is so close to the GPU that you can very quickly move stuff in and out of the processors, right? So whatever you put in your GPU memory, that's going to be the fastest to use. And then you have your main memory. Your main memory is going to be much further away. It's going to be next to your CPU, and it's called the RAM, the random access memory, right? And that is going to be much bigger, right? Generally, your main memory, you can have 128 gigabytes easy, but 128 gigabytes in your GPU, that's a pretty expensive GPU. So the main memory is going to be slower, but it's going to be much bigger than the GPU memory. So to efficiently use the GPU memory and reduce fragmentation, S-LoRA proposes unified paging. Unified paging uses a unified memory pool to manage dynamic adapter weights. We're going to they define a bunch of these terms later in the paper, so we're going to kind of go through some of these later. To manage dynamic adapter weights with different ranks and KV cache tensors with varying sequence lengths. Additionally, S-LoRA employs a novel tensor parallelism strategy and highly optimized CUDA kernels for heterogeneous batching of LoRa computation. This is like a salad of terminology here. Collectively, these features enable S-LoRA to serve thousands of LoRa adapters on a single GPU, right? Most of these cloud machines that you're serving on, right? So like if you go to AWS or GCP or Azure or any of these kind of like cloud providers, right? Generally the machines that they give you, at least the ones that you want to use, are basically going to have one GPU in them. You have machines that have multiple GPUs, but those are kind of more expensive. So if you can figure out a way to make it all work on these, or to serve your customers with these machines that just have single GPUs on them, especially cheaper GPUs that have less GPU memory, that's going to be a much more efficient way and much cheaper way to serve your customers. Compared to state-of-the-art libraries such as Hugging Face PEFT, which I think is literally this one, yeah, Hugging Face PEFT, which it might be the most popular one, and then VLLM, which is a different one, S-LoRA can improve the throughput by up to 4 times and increase the number of served adapters by several orders of magnitude. As a result, S-LoRA enables scalable serving of many task-specific fine-tuned models and offers the potential for large customized fine-tuning services. Right? So it's kind of, I think there's a lot of startups in this kind of world right now, right? Where basically you're taking something like the Llama 2 model, or you're taking something like the Stable Diffusion model, that's your base model, and then you're offering actual final intelligence kind of services to a customer who doesn't want to fine-tune, right? Fine-tuning is kind of complicated, and model serving is kind of complicated, and there's a lot of people who want to use Stable Diffusion, who want to use Llama for their application, but they're not technical enough to basically do the fine-tuning and serving themselves. So you're seeing a bunch of startups that are basically doing that for them. So all of these startups are going to have to do something like this if they don't want to just burn through all their money by having specific computers that have specific models on them, right? You want to be doing this. If all your models are based on Llama 2, you can serve them all using this architecture, or not architecture, kind of like system design. Okay, code is available here. If you want to try it out, they do have some nice code there. All right. We're going to kind of skim through this introduction here. Pre-train, fine-tune, scaling, fine-tuning of a base model has numerous tasks. Address this, several parameter-efficient fine-tuning methods have been developed, including the famous LoRA. One of the key innovations was the elimination of adapter inference latency by directly merging the adapter with the model parameters. So here they're talking about where you can take this BNA and merge it directly into the weights, and then basically you have the same inference cost, right? It'll basically be the same number of weights to support multiple models. The same paper proposes swapping adapters by adding and subtracting LoRa weights from the base model. While this approach enables low latency inference for a single adapter and serial execution, it significantly reduces overall serving throughput and increases total latency when serving multiple adapters concurrently, right? And this is kind of the key idea in this paper. So in this paper, and they're going to eventually show you why, they don't merge the LoRas. They realize that, hey, actually the way that this works out, if you only have one LoRa and one set of pre-trained weights, then yeah, merging them together is a great way to make this faster. But if you have thousands of LoRas, then merging it and then having to subtract it and then having to merge it again and then subtract it, that's going to be much slower. So it's actually better to keep them separate, right? So keep them separate, which is kind of initially it's kind of like, wait, why would that be better? But then in this paper, they're like, actually, this is going to work out, which is kind of cool. We study how scalable serve thousands of LoRa adapters. It is advantageous to separate the batchable base model computation from individual LoRa computations. Okay. Since GPU memory serving many LoRa adapters requires efficient memory management, since GPU memory is limited, we must store adapter weights outside the GPU and dynamically fetch them when needed, right? So they're storing these LoRas in the generic computer memory, right, the RAM, and then they're trying to bring them into the GPU memory. So you don't want it to be doing that constantly, right, because that's actually going to be kind of slow. coupled with dynamic allocation and deallocation of KV cache tensors for requests with different sequence lengths can lead to a significant memory fragmentation and I/O overhead. Okay, so maybe here let's take a little tangent to explain like what the fuck is a KV cache tensor, right? So this is here. So this is a paper that we read last week, and this is a paper called Fast Inference for Transformers via Speculative Decoding, and it's not super important, but there's really just one figure in here that I think really kind of shows you or starts to motivate this KV cache idea, right? So here they're basically showing you the inference or the time it takes when you're actually using this model for a encoder-decoder transformer, right? So an encoder-decoder transformer stack, right? And maybe let's do this. So this is your attention is all you need figure. You have the transformer in its original encoder-decoder pattern. You see this side here, this is called the encoder, this side here is called the decoder. So whenever you prompt GPT, right, the prompt and the system message, all that shit is coming in here, and it's going into the inputs here, and it's getting encoded, and then the actual output, right, is basically going in one token at a time. So the decoder is going to end up happening a lot more times, right? So the decoder, you see here, MP decoder, this purple blocks, there's a whole lot more purple blocks than there are yellow blocks, right? And every single one of these purple blocks, every single one of these decoder steps uses the same KV from the encoder. So you see here how the encoder has self-attention. So you see here this multi-head attention. These are the Q, K, and V matrices. This is self-attention, where that's just attending to itself. But here, the decoder, it has cross-attention, and in cross-attention, it's taking the cues from itself, which is from whatever it's outputted previously, and it's doing attention with the KV matrices from the encoder. So you can see here how it's only the KVs. So if you're going to be doing a whole lot of these purple inferences, a whole lot of these decoders, which you're going to have to do for every single token, you kind of don't want to have to calculate this part every time, right? You want to just store this KV. You want to cache KV. Caching comes from the French word caché, which means hidden or stored, right? And it's basically just a fancy way of saying I'm keeping these, I'm saving these for later, I'm storing them. So you want to cache or store these KV values here so that you don't have to constantly do this yellow part, right? You do this yellow part once, and then you store that KV, and then you basically use that same stored KV for all these little purple parts. Okay, so that's KV cache, right? And one thing to note is that the KV cache is actually quite big. So here, this is a different paper, which they actually reference in the S-LoRA paper, but here you have an NVIDIA A100 GPU. So this is a GPU with 40 gigabytes of NVIDIA or GPU memory. So this is the memory that is on the GPU itself. So you can see that whenever you're performing inference, so whenever you're serving or performing inference with a language model on this NVIDIA A100, the original model is this here. The KV cache is actually a big chunk of that, right? So you can see how it's actually kind of a significant chunk of that. The memory for the KV cache is deallocated per serving request, right? So every single customer is going to have a different request, a different prompt, which means it's going to be a different KV that comes through here, right? Everybody's going to have a different set of questions, a different set of system prompts. So that means that this KV is going to change per customer. And that's kind of an issue, right? Because it means that every single time you're performing inference, you're going to have to load all this KV back on there, then take it all out, and then load it back on, then take it all out, then load it back on, and so on, right? So that's a problem. What are we going to do about that? Okay. Leveraging multiple GPUs on a single machine requires novel parallelism strategies to accommodate added LoRa weights and computation. So maybe a note on multiple GPUs and parallelism. So what do they mean here by parallelism strategy? So parallelism comes from this word parallel, which means like two lines that are like that, right? That don't touch. And parallelism is the idea of more doing things in parallel, which basically means doing things at the same time and specifically on multiple different computers or multiple different GPUs and so on. So I think this is possibly the simplest explanation of, for example, two types of parallelism, one called data parallelism and then one called model parallelism. So in data parallelism, here you have device 1, device 2. Think of this like the GPU number 1 on your computer and then GPU number 2 on your computer. So in data parallelism, you're separating your data. So you're doing maybe just the first two parts of your right, the input, the data. You're separating that across devices. In model parallelism, right, you're separating the model into the two devices. So you're separating this W here. You're cutting this W in half, and then you're putting one half of it on one GPU, and then you're putting the other half of it on the other GPU, right? And there's advantages and disadvantages to both of these, and it's a very complicated situation, right? Because there's also other types of parallelism. There's tensor parallelism, and all of these types of parallelism there isn't like one solution that works for everything, right? If you have 3 GPUs, it's going to be a completely different thing. If you have 3 GPUs and then 2 of them are in faster interconnect speed, it's going to be a different thing. So like the nuances of parallelism it's like basically a fractal of like, you can never do this once, right? It's basically like this infinite optimization problem where it's going to depend on the hardware, it's going to depend on the model, it's going to depend on the data, it's going to depend on whether speed is more efficient. Like there's so many different variables that go into that it's kind of like there isn't one solution to fit everything. You have to basically figure out what's best given your hardware and your particular model and your particular type of application. So, okay, that's parallelism. And there is a person on our Discord channel, I feel like I need to call them out, but there's this person called Neuralink who is really into this type of shit. So Neuralink constantly posts us updates about all the learning that they're doing about parallelism, tensor parallelism, sequence parallelism. So if you're interested in talking about parallelism, or if you have any questions on that, definitely drop by the Discord and call out Neuralink, because they'll be happy to talk to you about that. I don't even know if it's a real human. It might even be a bot for all I know, but definitely obsessed with parallelism, so they can answer all your questions. To this end, we introduce S-LoRA, a scalable LoRa serving system. S-LoRA exploits batching opportunities, efficiently manages both host and GPU memories, orchestrates parallelism across multiple GPUs. Okay, so the primary contributions are as follows. Unified paging. To reduce memory fragmentation and increase batch size, LoRa introduces a unified memory pool. So they'll explain this a little bit later down, but this pool manages dynamic adapter weights and KV cache tensors by using a unified paging mechanism. So maybe just a sneak peek, but basically what they're going to end up doing is they're going to end up using a shared memory pool for both the KV cache and the adapter weights, right? So if we remember from this one here, right, the KV cache is a significant part of your memory usage. So they're going to say, hey, can we do something more clever where the KV cache and the LoRa weights, these adapter weights, are all kind of stored in a more unified memory pool, such that maybe we can squeeze out a little bit more performance there, right? Or exploit batching opportunities. Exploit opportunities where you could have batched things together because it was all in the same kind of like memory pool. Heterogeneous batching. To minimize the latency overhead when batching different adapters of varying ranks, S-LoRA employs highly optimized custom CUDA kernels. These kernels operate directly on non-contiguous memory and align with the memory pool design, facilitating efficient batched inference for LoRa. Okay, so what the fuck is a CUDA kernel, right? So one thing, is selecting the question from Josh. So is selecting the adapter token batch. Oh my God, I hate that I can't read your questions because there's this little thing, this little heart. Is selecting the adapter by token batch or by user query? I think they split it by token, but that's just me kind of skimming through this paper. I think we're going to have to read through the rest of this to answer that question, Josh. Okay, so highly optimized custom CUDA kernel. So I have here pulled up a live stream of this guy called George Hotz, who programmed basically his own PyTorch, you can think of it, called TinyGrad. And I really like this screenshot because it shows you kind of what's really going on here, right? So for all of us normies, right, we usually live in this world. We live in this world here, this Python world, where you're sitting and you're writing your neural net in Python code, right? But this is not the real world, right? What you're dealing with and what we're living in is just an abstraction. It's an illusion, right? You're living in this illusion world of Python where you're just like, I'm going to take this and multiply by this, and it just comes out like this, and great, and then I'm going to take that and multiply by this. Like, that's not the real world. The real world is this over here, right? This over here, these are the actual kernels, right? So whenever you create your little Python code here for your neural net, what's actually happening is that's going to then be turned into a compute graph of individual kind of operations that your GPU knows how to do called kernels. And those kernels are what your GPU is actually running, right? And most people don't really know what kernels they're running, right? They're living in this Python world, and then it just kind of magically poops out over here, and then you just have these kernels, and whatever works. But what people like George Hotz and the people who live in this kind of like custom CUDA world are doing is that they can look at these and say, hey, wait a second, over here, this kernel and then this kernel and this kernel, that's not actually efficient. There's actually a better way of doing that. There's a better way to do that, right? So this is kind of like a dark art, but if you're good enough at this kind of low-level programming, you can look at these things and as George Hotz does here, literally hand optimize a ResNet 50 and come to the conclusion that, like, hey, some of these kernels are not necessarily done in the correct order of operations here, and there's a faster way to do that. But most people don't live in that world, and kind of something that I brought up here just to give you an idea of what's going on is I'm kind of like bringing you guys all over the place here, but this is a kind of a clip from a movie called The Founder. So this is a great movie. I would recommend it. It's a movie about the McDonald's founder, and it has Nick Offerman in it and everything. But there's this scene where basically they sit here and they draw the like layout of the kitchen, and then they have people going and sitting here and going, and then they figure it all out, and they're sitting there and they're like, oh wow, look at that. If we put the fry cook next to the thing and then next to the front counter, then it's way less efficient than if we put the griddle next to the fryer next to the fridge, right? So this is that. There's this kind of world, but for programming, right? Most people don't live in this world. I don't live in that world. I don't think about the kernels and the ops that I'm using when I write my Python code. I just write my Python code, and then I just trust that some nameless engineer who committed to PyTorch and maybe works for NVIDIA like made it all work out. But there's people who live in this world, and they're kind of thinking like this, except rather than griddle and fridge and location, what they're thinking about is like the GPU memory cache, the L1 cache, this GPU memory register, the RAM, the CPU. So there's a lot of performance juice to squeeze because, kind of as we were saying before, there's kind of like an infinite problem space, right? You're never going to figure this out. You're never going to figure out the best layout for your kitchen, because even if I just change the number of fryers, or if I change the number of people that order burgers, or if I change the size of this office building or this little building, it's going to require a completely different solution. So kind of there's this extremely hard problem that is never going to be solved of like, how do I efficiently map the computation that I want to the hardware that I have, right? So in this paper, in order to implement this S-LoRA, where you have you want to keep your KV cache together with your LoRAs and then serve them in a very efficient, optimized way, they have to go all the way down to the metal and write their own custom CUDA kernel specifically to do that. Yeah, I'm with you, Ed. I'm scared by CUDA. I just live in Python world, and I just sit there nice and comfy as well. Okay. And then I guess the final contribution here, S-LoRA TP. To ensure effective parallelization across multiple GPUs, S-LoRA introduces a novel tensor parallelism strategy. This approach incurs minimal communication cost for the added LoRA computation. So minimal communication, right? Communication, you can kind of think of it like if you have your computer memory here and then you have your GPU memory here, it's like how much communication is there happening between that, right? So like communication between different parts is going to happen at different speeds. So you have to be very aware of that and see which parts are actually fast to communicate and then which parts are a pain to communicate. This is realized by scheduling communications on small intermediate tensors. Okay, so I guess they figure out that basically you want to do small, little tiny communications rather than big communication steps, and fusing the larger ones with communications of the base model. Okay, so they're going to be doing all of this for Llama, so they're basically just using Llama LoRas, but you could use this. You could do the same exact thing for this Hugging Face, right? Any LoRa, any model, any modality would work with this, although of course you're going to have to kind of massage it to fit your particular use case. S-LoRA can enhance throughput by up to 30x, and this is just kind of showing you just how crazy the speedups you can get here. Like, even for HOTS, right? Like, he's basically like he's not a one-man team. He's got like kind of a little open source community around him, but like he gets these kind of speedups all the time. He gets like 10x speedups, 20x speedups, right? So this stuff is not that efficient, right? Like, it's a lot of times these the actual code that you're running on your GPU is very inefficient. So there's a lot of opportunity for literally orders of magnitude, right? So it's not like we're talking about like a 1.1x speed up, right? Like, we're talking about orders of magnitude speed up if you just take the time to go into the actual kernels and be like, wait, is this actually the best way to do this? S-LoRA can improve by up to 4x and increase the number of served adapters by several orders of magnitude. Pretty badass. Okay, so background on LoRas. We kind of already have looked at this, but they have basically the same thing. You have your weight matrix, you have your AB, your two low-rank matrices, which form the LoRa, and then you can either merge them together, as you're doing here, or you can keep them separate, which is what they do in this paper, and they keep them separate because they kind of will go to show you that it's actually a much faster way of doing it if you're serving a bunch of LoRas on the same node. Okay, serving large language models based on the transformer architecture, blah, blah, blah. Several inference process requires iterative autoregressive decoding. So this is what we were looking at there, right? Iterative means multiple steps, multiple iterations. Autoregressive means that you're looking at your own, you're auto-regressing, you're looking at your own output, and then you're decoding. So that's literally what a transformer model is doing, right? It's auto-regressively. It's looking at its own output. So this decoder here, which is the purple block, it keeps looking at what it keeps putting out, right? So it's like it's putting out one token at a time, but it looks back at all the tokens that it's put out. So that's the auto-regressive decoding. Initially, the model carries out a forward pass to encode the prompt. So that's this yellow part here, right? That's the encoding. And once you encode it, then you get the KV cache, right? Follow this, it decodes the output token one token at a time. The sequential process makes decoding slow. Since each token attends to the hidden states of all its preceding tokens, it becomes essential to store the hidden states of all previous tokens. And that's the KV cache, which we saw before, right? You KV cache, this is the little KVs that come out of the encoding, because you really only want to run this yellow part once so that you can then keep doing these purple parts with the KVs that you stored from this yellow part. Such a mechanism adds to the memory overhead and causes the decoding process to be more memory intensive than computation intensive. Okay, so here they're kind of lamenting this a little bit, right? Because they're saying, okay, well, yeah, you can store everything in the KV cache like they're doing here, but then it means that you're going to have to basically unload this KV cache and put a new one in if you're getting a customer that has a different thing that they encoded. Or if you're trying to load a LoRa, maybe the LoRa doesn't fit, and now you have to take this KV cache out to put the LoRa in to then put the KV cache back in. So like, they're realizing like, hey, you're maybe potentially trading off computation intensive things, memory intensive things, and then communication overhead as well. Okay, blah, blah, blah. There's a couple different ways that people have tried to get this to work. There's Orca, there's VLLM. So VLLM is actually the paper that I have pulled up here. When serving very large models that exceed the memory capacity of a single GPU, or when there are stringent latency requirements, it is necessary to parallelize the model across multiple GPUs. So this is model parallelism, right here. You're splitting the model into two parts, putting one on the first GPU and the other one on the second GPU. And there's a bunch of other fancy types of parallelism, and drop by the Discord and ask Neuralink about those. But let's look for a second at VLLM, this one here. We build VLLM. a LLM serving system that achieves near zero waste in the KV cache memory and flexible sharing of KV cache within and across requests to further reduce memory usage. Okay, so this paper, kind of a lot over token stays. I think there's one thing here that I wanted to show. Yeah, okay, here we go. So here you have the VLLM system overview. So you can see here how you have different workers. Each of the workers has a different GPU, and you can see how they have a model parallelism here where they have model shard 0, model shard 1. A shard is basically like the same way that you would take a stone and then you would break the stone into shards, right? Shard is basically an English word for like a broken piece of stone, right? So model shards is basically a little chunk of the model. So here they're splitting the model across the GPUs. And you can see here how there's this scheduler now. And the scheduler has access to the GPU memory and it has access to the CPU memory, and it's being clever about the KV cache and saying, okay, well, this worker 1 only has this part of the model, therefore I don't need to give it the entire KV cache. I probably only need to give it a subset of the KV cache, right? So what this VLLM is doing, and it does it in kind of a more complicated, convoluted way, but it's basically, it's all based on that. The fact that because the model is sharded across different GPUs, you don't need to have the full KV cache in every single model. You can basically just have only specific parts of the KV cache given to that specific GPU, which only has part of the model, right? And then you have this scheduler, which does all the kind of routing for that, right? So that's what VLLM is, and S-LoRA is basically kind of building on that work. Overview of S-LoRA. S-LoRA encompasses 3 principal components of innovation. Blah, blah, blah. Introduce batching, which decomposes the computation between the base model. We address the challenge of request scheduling. Ability to batch across concurrent adapters. Generalize page detention. Okay, I think they're just kind of summarizing what they're doing. Let's look at batching. Our batching strategy aims to support online and high throughput serving of many LoRa adapters simultaneously. For a single adapter, the method recommended is to merge the adapter weights into the base model, right? So if you only have one LoRa, just fuse it into the base model and then you're good to go. Just serve that base model as you would. This has the advantage that there's no additional adapter overhead during inference, since the new model has the same number of parameters as the base model. In fact, this was the prominent feature of the original LoRa work. However, when there are multiple adapters, merging the weights into the base model leads to multiple weight copies, missed batching opportunities, right? Because now you have maybe 5 computers, each with their own GPUs, and if you were to actually look inside each of those 5 computers and the GPUs inside each of those 5 computers, they would basically have the same, a lot of the same weights, because the LoRAs are really only applied to parts of the model, right? So here, right, the LoRAs are it's not like the LoRa is, or there's LoRAs for every single part of the model. The LoRAs are only applied to some subset of the model parameters. So if they're only applied to some subset of the model parameters, then you're going to have a bunch of computers that have the same exact model weights with just a slightly different LoRa, or a slightly different model weight on the part where you merged in the LoRa. In the original LoRa papers, the authors proposed adding and subtracting LoRa weights on the fly, which could be one way of doing it, right? The same way that you can merge in the LoRAs, you could then just subtract them out and then add a new one in. But then you're going to be doing a bunch of matrix add and then matrix add with a negative. So it takes like a CUDA bro to realize that, hey, adding and subtracting is actually cheaper than not adding it to begin with and then doing it separately. And therefore limits batching opportunities. Okay, what do we got here? Separated batch computation for the base model and the LoRa computation. So here you have X. X is basically this. It's the original weights of the model. You can see here how batched base computation, so the original base model, you're multiplying, or no, X is the input, sorry, W is the weights. So W is the weights, you're multiplying the input by the weights, and that's giving you the final output, right? Batched LoRa computation, these are the LoRAs, so here your A, B matrices are the LoRAs. Notice how they're smaller than this W. And you're multiplying the parts of the X that are specific to that part of the LoRa and then adding it at the end, right? So you're doing the computation separately and then adding it here rather than merging the LoRAs in and then doing the computation once. Batch computation of the base model is implemented by GEMM. The batch computation for LoRa adapters is implemented by custom CUDA kernels, which support batching various sequence lengths and adapter ranks. Okay, so GEMM, and this is another little tangent here. I had to look this up, but GEMM is a implementation of the operation C equals A times X plus B. So basically, the GEMM kernel is, I think, is generalized general matrix multiply. It's like basically the most common or basic type of kernel that you could have, right? So it's like one of these kernels, right? And BLAST stands for Basic Linear Algebra System or Library or something like that. I don't know. But if you're doing a matrix multiply, this is largely what's happening, right? And here you have the L1 gem. So L1 is going to, the memory caches are going to be named. Usually L1 is the memory cache that is the closest. I think there's actually an L0 sometimes, but L0 is going to be closer than L1, which is going to be closer than L2, and so on, right? And here's actually the primitive operations that are happening here. You have this transpose, you have a double buffer, you have a systolic array, and I had to look that up, but systolic array comes from the heartbeat. So in your heartbeat, you have cardiac cycle, right? So here's basically how your heart works, and it basically there's two parts of this. There's what's called the diastole and then the systole, right? So the same way that and the way that your heart works, right? It's kind of like moving blood into these chambers, and then it's moving blood out of the chambers, and then it's moving into here, and then out, and then here, and then out. So the same way that you have this kind of like repeating multi-step process for your heartbeat, which is called systole diastole, someone took that same name and called the arrays of processors inside a chip a systolic array. So a systolic array, here you have a TPU, which is Google's tensor processing unit. It's basically Google's GPU, right? It has this same kind of like systolic flow, right? Systolic data flow, where like there's a part where all the data is coming in, all the blood is coming into the chip, into the processors. You have a bunch of these processors that are all doing their chink chink, you know what I'm saying? They're all like chunking at the same time, like chink chink, calculating, and then all the data flows out. So it's kind of like a heartbeat where it's kind of like this alternating cycle of like shit comes in, then you do your computation, and then shit comes out, right? And that's where the terminology of systolic array comes from. And that is what systolic array in the GEMM kernel is, and the GEMM kernel is the kind of basic kernel that you use for this matrix multiply up here, right? But in this paper, right, they're not just going to use the GEMM kernel for this, they're going to use a fancier custom CUDA kernel for that. All right, what do we got here in figure 2? All right, so figure 2, overview of memory allocation in S-LoRA. S-LoRA stores all adapters in the main memory and fetches the active adapters for the current batch to the GPU memory. Okay, so S-LoRA is basically doing this fetching, right, similar to the paper here, right, where you have this scheduler. So the scheduler is being clever about which things it gets from the main memory, which is the RAM, to bring into the GPU memory. So that's what's going on here. The GPU memory is used to store the KV cache, adapter weights, base model weights, and other temporary tensors. So here's your KV cache, here's your adapter. You can see how on the GPU memory you have the KV cache, which is actually a big block, and then you have these different adapters, and then your S-LoRA is going to be clever about how it fetches these adapters. And then you have, of course, your base model weights, which are the W's here, and then any other temporary tensors that you might have. Okay. Let's keep going here then. Base model is inefficient for the multi-LoRa high throughput. This avoids weight duplication and enables batching of the more costly XW operation. However, because the cost of XAB is substantially lower than XW and there's a considerable amount of savings from batching XW across different adapters, we show that savings far exceed the additional overhead. Right? So it's kind of like this non-intuitive solution. A lot of these CUDA kernels basically come down to that, where it's like you realize that like, hey, rather than doing this 10 times and then this, why don't we do this once and then we only have to do that other thing once, right? So it's this constant like pull and push kind of like trade-off of like, is it faster to communicate more and then do a bigger batch of things, or communicate or is it faster to communicate less and do a bigger batch of things, or is it faster to communicate more and do more things in a smaller batch? I'm like slipping all over the place here. Unfortunately, directly implementing the factored computation of the base model in individual LoRa adapters using the batch GEMM kernel would require significant padding and result in poor hardware utilization. This is because of the heterogeneity of sequence lengths in adapter ranks. So what are they talking about here is that the sizes of these are a little bit weird, and the GPUs themselves, right, they have some specific size, right? So kind of like how your heartbeat has some specific volume of blood that it's very good at pumping in and out. The GPUs also have some specific size of numbers that they're good at multiplying, and then some specific size of data that comes in and data that comes out, right? So you don't want to have a mishmash of things that you want to calculate where sometimes you have a big volume of blood and then sometimes you have little tiny volumes of blood, right? You don't want to be like pumping or spending an entire heartbeat for just a little tiny volume of blood, because then you're just wasting a heartbeat, right? So like you really want to pack out all of the parts of that. You don't want to be doing where were we? I think we missed. Yeah, we were here. Never mind. Sorry. We don't want to be padding a bunch of weirdly shaped tensors and result in poor hardware utilization. In S-LoRa, we batch the computation of the base model and then employ CUDA kernels to execute the additional XAB for all adapters separately. This process is illustrated. Instead of natively using the blast padding, we use the custom version. While the number of LoRa adapters can be large, the number of LoRa adapters needed for currently running the batch is manageable because the batch size is bounded by the GPU memory. To take advantage of this, we store all LoRa adapters in the main memory and fetch only the LoRa adapters needed from the currently running batch. The maximum number of adapters that can be served is bounded by the main memory size. And this is important too, right? Because when you're buying GPUs on the cloud, right, GPU RAM is much more expensive than just RAM, right? You can probably get a computer that has much more RAM for a significantly cheaper price than you can get the same computer, but with a GPU that has more VRAM. So if you can exploit that much cheaper RAM, as opposed to just kind of cramming everything in the GPU RAM and then just using the biggest GPU possible, you're going to save a bunch of money. To achieve high throughput, we adopt iteration level scheduling batching strategy. Requests are scheduled at the token level. So here, they're scheduled at the token level. What they're saying here is that, right, every time you decode here, right, this is token level because the decoder is happening on every token. So the batching, right, or the clever scheduling, right, where you're kind of being clever about what to put in, what to take out, that is happening at the token level. So it's happening in between each of these little purple blocks, right? So I think that maybe answers your question, Josh, where you were asking whether they do it at every token or every user query. They're doing it at the token level. So they're batching, they're figuring out the best things to put at the token level, which is kind of crazy, right? You would have thought that token level would have been just so much overhead, right? If you have to do it at the token level, you're constantly communicating, but for the way it all kind of magically works out, doing it at the token level is actually faster. The request will exit the batch once it reaches the maximum number of generated tokens or fulfills other stopping criteria. This process reduces GPU memory usage but introduces new memory management challenges. Okay. To enhance batching efficiency, one potential strategy is reducing the number of active adapters in a running batch. Using fewer adapters, there's an opportunity to allocate more memory to the KV cache. So there's this kind of trade-off, right? Like, do we have more adapters or more KV cache on our GPU memory? Given the common memory capacities, they're often underutilized while decoding. This is kind of cool, often underutilized. Maybe this is just the case for LLMs. And this is another thing too. It's like the compute workloads for language models are different than the compute workloads for images. Like images are just bigger chunks of data, right? So like you end up getting different types of compute patterns when you're dealing with images or videos than when you're dealing with text. So some of the intuitions and kind of like high level rules of thumb that they talk about in this paper might not be applicable to everything else, right? It might just be that they work out for language models, but if you were to try to do this with a vision language model that had a 32 frames of video, it might not work out that well. A direct approach to reducing the number of adapters is to prioritize batching requests that use the same adapter, a strategy we term adapter clustering. Okay, so that obviously makes sense. If you have users that all want to use the same LoRa, right? You have a bunch of users that all want to use the same paper cut LoRa, right? You want to batch those requests together and then do that inference at the same time, right? So in this case, they're doing everything with Llama LoRa. So it's like, I don't know what LoRas exist for Llama. I think you probably have like a JSON Llama, and then you have like a robot action Llama. I don't know what people do with language models. I think this kills mixture of LoRa trying to see if they have some sort of router, not clear how they are selecting the adapter. I think the adapter is selected by the user. So I think the adapter is whatever the user actually wants, right? So like, if you have a bunch of people that are requesting from your custom fine-tuned website, right, you might have 10 people who want to interact with the French poetry Llama, and then you have 3 people who want to interact with the German poetry Llama, right? So you would want to batch all the 10 people that want to use the French poetry LoRa and all the 3 people that want to use the German poetry LoRa. So the LoRas, or the adapters that you want to use, are coming all the way from the customer, but then in terms of like the individual token level optimization, at that point, then it's like, okay, I have these requests that I need to fulfill, these things that I need to serve. How am I going to serve them efficiently? Adapter clustering comes with its own set of trade-offs. It can hurt the average latency or fairness amongst adapters, right? So if you over-optimize too much, then maybe that one guy who wants the LoRa for Swahili poetry is just sitting there waiting for like 10 seconds because this optimizer never loads the Swahili poetry LoRa because he's the only person who requested inference from the Swahili poetry LoRa. So you have to have kind of bounds or like guaranteeing some amount of fairness amongst these adapters so that you would do eventually serve even weird compute requests. Okay, in S-LoRA, we applied an admission control strategy to sustain good attainment when the traffic is higher than the serving system capacity. Serving system is typically characterized by service level objective, which specifies the desired latency of processing requests. Okay, so service level objective is some project manager comes and he says, okay, well, when they're using this website, the maximum someone can wait for their poetry LoRa is 5 seconds. Okay, so we're going to say 5 seconds is so some arbitrary desired latency. If the serving system has fixed capacity, it must implement an admission control mechanism that drops a request if the system cannot meet its SLO. Otherwise, if no request is dropped, blah, 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 serving system is bound to violate. We implement an abort strategy to mimic admission control in S-LoRA called early abort. Intuitively, we estimate the set of latest requests that we can serve and then serve them in the order of arrival time. Okay, so this is kind of cool because it's just they're just trying to show you how like their scheduler is actually accounting for a lot of interesting things, right? It's not just accounting for, hey, I want to utilize my memory as efficiently as possible. It's not just accounting for, hey, I want to do this in as few steps as possible, right? I want to batch as much as I can, but it's also keeping track of like, hey, when did this request come in and how long has it been since this request come in and can I put this one in right now, right? So it also has like multiple different things that it's optimizing over in terms of figuring out exactly what is going to happen in this exact systole of the GPU, right? The GPU is sitting there just pumping that blood, and it's going to figure out exactly what's going to go into this next blood pump. Okay. Memory management. Let me take a little sip of water. Maybe you guys have a second to ask some questions here. I'm thinking about how blockchain works with multiple nodes, and it can be applied to the way KV cache and adapter. It would be fantastic. Yeah, there's probably all kinds of crazy shit you can do with like a GPU blockchain. I don't know very much about blockchains, but I bet you that there's definitely smart people thinking about that, because I know that it's very slow, right? That's one of the things that people complain about, is that the Bitcoin blockchain is like incredibly slow because you have to mine that stuff, and then it even has a very small size, right? Every single block in the chain, it has a limited size, so there's a limited amount of stuff that you can fit in that block. So I don't see why you couldn't insert a router here and basically get swappable mixture of experts. Yeah, I mean, you could probably figure out all kinds of fancy shit to put in here, right? Different experts, which are each of them a LoRa. To support many adapters, S-LoRA stores them in the main memory, loads them into GPU RAM. There are two noticeable challenges. The first is memory fragmentation, resulting from the dynamic loading and offloading of adapter weights in various sizes. So I think they've mentioned this a couple times, but here they're talking about memory fragmentation. They also mentioned up here non-contiguous memory, right? So memory pools, like what the fuck are they talking about? So what they're talking about is that the memory itself, right, is not just one giant place, right? Think about the memory kind of like a corporate campus, right, where you have different buildings in different places, and some buildings are kind of far away, some buildings are closer, and non-contiguous memory is memory that's not together, right? That's like if you had people who are all part of the same team, some of them are working in this building and some of them are working in that building. That's non-contiguous memory, right? You don't want to memory fragmentation, right? You don't want to have like things that are fragmented all over the place, right? Ideally, you want things that are related, close together in the same place in the memory, contiguous, right next to each other, or you want them at least close, right? So if you have everything in this giant memory pool, you could end up in a place where things are kind of like unnecessarily far apart. My nose is just itchy. Sorry, wait a second. I'm going to blow my nose here. Okay. Second is latency overhead, blah, blah, blah. Tackle these challenges, propose unified paging. What is unified paging? Understanding the nature of adapter weights is essential for optimizing memory usage. Our primary observation is that these dynamic adapter weights are analogous to dynamic KV caches in several ways. Variable size and operations. Just as the size of the KV cache size fluctuates with the sequence length. Okay, what does that mean? So, right, the KV cache is coming from this, but the KV cache is really the encoded prompt, right? So people are prompting with different lengths of sequences, right? Maybe I just say, hey, what's the answer to 3 plus 4? And then someone else is like copy pasting a whole book and saying like, hey, what's the next token in this book, right? So like different requests are going to have a different size of KV cache. So the KV cache is going to depend on the user request, and that's going to depend on the sequence length, or the sequence length, which is the user request, sorry. The ranks of the active adapters can also depend on the choice of adapter associated with each request. KV caches are allocated when requests arrive and deallocated when the requests are completed. Similarly, adapter weights are loaded and cleared with each request. If not managed properly, this variability can result in fragmentation. Okay, and here is, I think, the most important part of this entire paper, and the entire reason. I think this is what they realized, and then from this grain of truth, they eventually came to this whole paper. So here it is. Here's basically the TLDR. A KV cache tensor for a request in a layer has a shape of S and H, where S is the sequence length, right, which is the prompt. How many tokens is my sequence, or is my prompt? And then H represents the hidden dimension, which is basically the little vector that represents each token, right? That has some specific H dimension. Meanwhile, the shape of a LoRa weight is RH. R standing for the rank, and then H for the hidden dimension, right? Both share a dimension of size of H that can be leveraged to reduce fragmentation. And that sentence right there, both share a dimension size of H that can be leveraged to reduce fragmentation, that's this entire fucking paper. Basically, what this paper is, and here you have a figure 3, a unified memory pool, is, hey, actually, these LoRa matrices are of dimension R by H, and then the KV cache is of dimension S by H. Holy shit, that means that we can put them in the same unified memory pool. We can put them in this same building, and the basically the desks are the same size. You know, like kind of it's like, oh, holy shit! It turns out that the deep fryer is the exact same width as the fry cooker, so we can basically put deep fryer, fry cooker, and then fryer cooker. You know what I'm saying? So that's basically kind of the magic trick that makes all of this possible, is that because both the KV cache and the LoRas have this shared dimension of H, you can store them in a unified memory pool and store them in a non-contiguous way to reduce memory fragmentation. The page size is H elements, where H is that shared dimension. And there you go, guys. That's how all the magic happens. And I don't actually know. I don't know who these guys are. I don't know who the people who published this paper is. But I would suspect that that's actually probably how this paper even started. Is that they came to this realization, and then we're like, holy shit, let me try something, and then there you go. Now you have this paper. Motivated by these parallels, we extend the idea of paged attention to unified paging which manages adapter weights in addition to the KV cache. So basically, they took this paper, which was like, hey, you have this KV cache, and they're like, hey, rather than just scheduling the KV cache, why don't you also schedule our LoRas, because our LoRas are the same fucking size. To implement this, we first allocate a large buffer statically for the memory pool. So if you guys work in Python, you might not know this, but big boy programming, where you actually have to allocate your own memory, right? You have to, before you even run your program, you have to basically say, okay, I'm going to allocate this chunk over here, this building over here. It's empty right now, but I'm going to be putting shit in there. You're not allowed to touch it, right? So you're allocating a specific part of your memory to this pool. So it's going to be some fixed size, which you decide at the beginning. Allocated a large buffer statically for the memory pool. Why is it still green? I want yellow. Yellow. This buffer uses all available space except for the space occupied by the base model weights and temporary activation tensors. Both KV caches and adapter weights are stored in this memory pool in a paged manner, where each page corresponds to a vector of H, right? And the vector of H is coming from the fact that they're doing this per token, right? So the requests are scheduled at the token level. Each token is going to have is going to be of dimension H, which means that the paging, right? Paging, think about like literally paging through a book. You're going through it page by page. So this blockchain, or this block of memory, is paged according to that dimension H. Thus, a KV cache tensor with a sequence of length S uses S pages. A LoRa weight tensor of rank R uses R pages. Figure 3 illustrates the layout of our memory pool, where KV caches and adapter weights are stored interleaved and non-contiguously. What they mean by that is, if you notice up here, it's not like all your KV caches are up here and then you have all your adapters. They're interleaved together, right? So you have KV cache, empty, adapter, KV cache, empty, KV. So it's like you just have this generic slush pool where you're just kind of like throwing in LoRa's and throwing in KV caches. Blah, blah, blah. Prefetching and overlapping. Although the unified memory pool mitigates fragmentation, the I/O overhead from loading and offloading remains a concern, right? So this is the trade-off, is that, okay, now we put everything into this giant pool of memory that's sitting at the GP or at the RAM, right, on the computer. But now we have this fucking giant pool of memory sitting in the RAM, and every time we want to do anything, right, which is every single token, every single time we decode a token, right, one of these purple, we're going to, in between every single one of these purple blocks, we're going to have to go to the CPU, say, hey, what's in your memory? Hey, give me this thing in the memory. Okay, and then bring it back to the GPU. So this I/O overhead, or input-output overhead, it might be a huge problem, right? So how are we going to deal with that? The latency introduced by waiting to load these adapters can compromise the efficiency of the system, right? And this is maybe a little tangent here. So like, there's a fuck. I'm trying to like think about the exact wording that I need to type this. NVIDIA GPU China requirements or something like that. Let me see if I can find this plot. If I find it, it's gonna be crazy. NVIDIA GPU China State of AI report. Fuck. All right, give me one more second here. I'm going to try to find this. No, okay. I won't find it. Okay, but basically what I was trying to say is that, right, this latency, one way to answer with that latency is that there's basically these interconnects, right? So like inside these chips, right, you can mess with the volume, right, the actual number of processors, but sometimes it's not actually the size of the or the number of processors that matters, right? It's not like the actual volume of blood in the heart. It's like how much you can actually pass. It basically comes down to these interconnect speeds, right? Like how much data can you actually pass through at a time. And one way to make TPUs and GPUs faster is by having the actual number of processors increase, right? Just make each pump bigger, right? So it can basically fill like a whole bucket and then get rid of that whole bucket. But the other way to do it is to basically communicate information faster and make the whole thing just basically pass more things. So interconnect speed is a different way that you can make these things total volume go up as opposed to increasing the number of processors. So an interesting thing that NVIDIA has been doing is that the regulations around GPUs and TPUs are based, or they have specific requirements for the latency or the interconnect speed and then the number of processors or something like that. And then basically NVIDIA is making chips that are very fast interconnect and then chips that have a lot of processors. Obviously, some of you might actually be more aware of the nuance there and you're kind of cringing at what I'm saying, but it's interesting how like regulation is causing basically a bifurcation of the type of hardware, where one hardware is more about more throughput faster by faster communication and the other is more throughput faster by kind of just bigger chunking happening. I don't know. I thought that was kind of cool. I wish I could have explained it better, but maybe some of you will be able to explain it better on the chat. Okay, we run the current decoding batch. We predict the adapters required for the next batch based on the current waiting queue. This prediction allows us to prefetch and store them in available memory. Such a forward-looking strategy keeps most of the adapters needed for the next batch already in place before running it, which reduces I/O time for adapter swapping. Okay, so they're actually doing some even more clever stuff where they're like forward-looking, right? So the scheduler is aware of like all the inference requests that came in and knows when they came in and knows which ones need to be served first, which ones can wait a little bit to be served. And not only is it loading all the stuff into your GPU memory per token, but it's also doing this forward-looking where it's kind of like getting it ready a little bit to put into the GPU memory so that you don't have to spend too much time going to some weird part of your RAM just to bring it into your GPU memory. Due to the design of the unified memory pool, the adapter weights are stored in a non-contiguous memory. To run computations efficiently, we implement a custom CUDA kernel that batches this LoRa computation. In the pre-fill stage, the kernel handles a sequence of tokens and gathers adapter weights with different ranks. We call this kernel multi-size batched gather matrix multiplication, MBGMM. It is implemented in Triton, which I think I actually did mention in a previous stream, but it's a more open source effort, if I want to say. I remember when this came out, Triton GPUs, not the moon. Open source GPU programming. So kind of interesting because it basically means that you have off chip the DRAM. DRAM is the system memory, right? And then on chip, so this is on your actual GPU, you have your L1, which is closer to your core. The core is the actual processor. L1, that's going to be closer, and then L2 is going to be further away, so off chip. So TLDR, Triton is basically what the cool kids write CUDA kernels in nowadays, and it makes sense that they implemented this in Triton. Okay. Tensor parallelism. We designed novel tensor parallelism strategies for batched LoRa inference to support multi-GPU inference of large transformer models. Tensor parallelism is the most widely used parallelism method because its single program, multiple data pattern simplifies its implementation and integration with existing systems. I think here what they're talking about is single program, multiple data. Tensor parallelism can reduce the GPU memory usage and latency when serving large models. In our setting, the additional LoRa adapters introduce new weight matrices and matrix multiplications, which calls for new partition strategies. So tensor parallelism, right? I think it's a type of model parallelism, but you're splitting up the model across multiple devices, right? So you're doing different parts of the model on different GPUs so that you can do them in parallel at the same time so that the overall inference is faster, right? So I don't exactly know the distinction between model parallelism and tensor parallelism. I think tensor parallelism is a type of model parallelism, but I'm not 100% sure on that, so don't quote me. In the base model, we use Megatron LM tensor parallelism strategy. Our approach aims to align the partition strategies of inputs and outputs to the added LoRa computation, which those are the base model. In this way, we can minimize the communication costs by avoiding unnecessary communications and fusing some communications. Okay, we use the feed-forward module, 2-layer MLP, to illustrate our partition strategy. We will explain later how the strategy can be easily adapted to the self-attention layer. The upper box illustrates blah, blah, blah. Okay, so here we have the full compute graph for what the fuck is actually going on. Okay, so tensor parallelism partition strategy for batched LoRa computation. So you're trying to compute some inference with your LoRas, and it's batched, right? It's being batched by this scheduler. So here in your input, let's actually zoom in here so we can see a little bit better. So your input is of dimension b times h, right? So think of it as basically you have one token, or a batch size b of tokens of dimension h. So you have, actually let's highlight some of these. B is the number of tokens. H is the input dimension, right? And that's the dimension that's common between the LoRa and the KV cache. N is the number of devices, so how many GPUs you have. And then D is the hidden size, and then R is the adapter rank. So different LoRas have different size R, but the R is generally much smaller than the input dimension. Okay, so column partition, row partition. I think here what their column partition means you're splitting, the yellow is on one GPU and the blue is on a different GPU, right? So you can see here the dimensionality is H and then D over N, because each GPU, if you have two GPUs, then one GPU is going to have D over, it's going to have one half of the D, and then the other GPU is going to have the other half of the D, right? So that's why you have this over N here, because if you have three GPUs, then each GPU is going to have 1/3 of the D dimension here, right? So you can see here, every GPU has the whole batch, but it only has 1/3 or 1/2, depending on how many GPUs you have, of the D dimension. So you're splitting it, I guess in the column would be the way to think of it here. And then row partition is here. Here you see how the split is happening here. So you're splitting the D, and then every GPU has all the H, but they only have whatever 1/3, 1/2, however many GPUs you have of the D. Okay, so here's your W. Here's your matrix multiply, right? So your W is your actual weights. Your matrix multiply is this right here. When you're doing WX, that's your matrix multiply, right? That's where your GEMM comes in, right? So this is your standard GEMM. You have some input X, your matrix multiplying it with this W, right? If we actually look at this, right, that's probably, you want all that shit there. So whenever you're doing your actual matrix multiply or your GEMM on this little core here, you probably have all your W here and you have all your X here. So you have everything ready to go in this L1 SRAM, and then it gets thrown into that little heartbeat there, and then you get that matrix multiply, right? I call it like, I keep saying the word chunk. Chunk has a bunch of actual formal definitions, so I'm sorry if that conflicts in your mind, but whenever I say chunk, in my head I'm thinking about those like old school like cash registers, whenever you like hit them and then it goes and it goes back and it makes this like sound. So that's what I'm saying in my head when I say chunk. It's like, it's basically one kind of like beat of this like little GPU heartbeat. All right. But okay, you multiply your W's times your input, and now you need to add the LoRa. So you see how the LoRa, you have your LoRa's split across your GPU, so R over N, and then D over N. Here you have your splitting. And then you have this all gather, and the all gather is kind of tricky, right? So here you have replication, right? So what the fuck do they mean by this? So, oh my God, why is my mouse just fucked? 1, okay. Here you have replication, and there's a couple nodes here that are called replication. You have all reduce and then all gather. And what they're talking about here is that when you're splitting, when you're doing parallelism, right, and you're splitting that across multiple devices, sometimes you need to know what the other GPU did, right? So you might be able to perform a matrix multiply for a specific layer in your model, and the GPU over there is performing a different matrix multiply for a different part of the model, but then you get to the next layer, and you need to know what that other GPU over there did, right? Like, you can't calculate it all yourself. You need to get whatever it did. So there's a little bit of communication overhead, right, which is this all gather operation where you need to wait to get what that guy's doing, right? So that's that all gather. All gather means, hey, we need to all gather together to combine all of the answers that we individually computed as little individual GPUs so that the next computation can use our combined answers, right? And these can be basically kryptonite, because sometimes if what you're doing as a little GPU is much faster than what that GPU over there is doing, then you're going to be done much quicker, and you're going to be sitting there waiting for that other GPU to finish so that you can use the answer that it got to get you the next answer. So that's where this stuff can get very tricky very fast, because it's like when you're doing these fancy types of parallelism and you're splitting things across multiple GPUs, like sometimes the communication overhead, right, these all gathers, these all reduce, can basically just shoot you in the foot, because you might be waiting for one GPU that is the slowpoke that has to calculate a slightly bigger matrix multiplier. It has to do a slightly more like involved kernel, and because of that, you have like every other GPU just sitting there, just staring, just waiting at that other GPU to finish so that they can get the intermediate answer to get to the next one, right? So yeah, it's a very tricky problem. CUDA bros are built different. Okay, but then you have the LoRa, blah blah blah. Here's the next step. You add them together. Okay, fuse all together and all reduce. So here, this is where I think here they were saying, okay, we're going to be clever about the communication, and the way that we're clever about the communication is that whenever you're doing the all reduces and the all gather here for a bunch of different LoRa adapters, the way that we partitioned the LoRas across multiple GPU means that we can have a bunch of smaller communications, right? So this is kind of what they were saying here. All reduced communication is required to accumulate all the partial sums from all the devices. The matrices A and B are compartitioned. All gather operation is used to collect the intermediate results. The all reduce is used to sum up all the intermediate results. Finally, the result from the LoRa is added to that of the base model. A single all reduce operation is sufficient to accumulate the final result. It is worth noting that we are essentially fusing an all gather operation with a final all reduce. So that's the little bit of magic in the CUDA kernel, right? That's the little bit of magic that someone who sat there and stared at these fucking kernel ops and was like, hey, wait a second. It turns out that the KV cache and the LoRa kernels have this shared dimension H, and because I know they have this shared dimension H, it means that I can calculate these split across multiple GPUs and do it all and fuse together what would normally be a couple different all gathers into one all reduce. Which is like, how the fuck a human being even like it realizes these things and like implements that? Like, I have no idea how they do that. You know, that's like some fucking like 500 IQ level stuff there. Okay. Communication memory cost analysis. NB the number of devices, B is the number of tokens, H is the hidden size, R is the adapter rank. The communication cost of the base model is the all reduce, or is one all reduce, or 2 times blah blah blah. The communication cost of the added LoRa computation is 3 all gathers and 1 all reduce. right? So again, communication cost. So you have your cost of actually performing the operation, but then you have the communication cost of sending information back and forth between all these different basically distributed parallel systems or little GPUs, right? So the communication cost is your all gathers and your all reduce. And because of the way that the LoRa dimensionality works out, right? Because LoRa's, remember, they're not the same size as the original weight matrices. They're smaller because they have this low rank, they're a low rank matrix, which means that this dimension R is very small. It's basically like 1, 2, 3, 4, 5, something like that, right? So because R is significantly smaller than H, doing 3 all reduces and then 1, or 3, 3 all gathers and then 1 all reduce basically ends up taking less time than the 1 all reduce, right? Because this has H here and this is R here. You see that? So very tricky stuff here, right? They basically decided that, like, hey, the model is so much bigger than the LoRa that we could do a bunch of little LoRa computes and communicate back and forth 3 extra times, but because they're smaller and because the communication is smaller, because the total number of things there to communicate is smaller, that whole thing is going to happen basically in a less time than it would take to do the whole feed forward for the model. And because of that, we can now just keep the base model separate from the LoRa's and then serve all the LoRa's basically independent, having this scheduler that kind of loads them in a little bit more intelligently. So like the way this entire paper like all comes together is so cool. I just think it's pretty badass. And I'm like in awe, like to me it's like I can kind of like talk about kernels and talk about ops, but like I could not, gun to my head, I could not write a fucking CUDA kernel. So hats off, and like I'm super appreciative that there's people out there that can like sit there that close to the hardware, that close to the metal, and like come up with these kind of optimizations, because they're significant, right? It's like, it's kind of what I was saying before. It's like, these are not small peanuts. Like we're talking about like 30x improvements, like 30x throughput enhancement, So like, it kind of makes you think of like, yes, the people who do this are very smart, but they're still humans, right? So like at some point we're going to have AIs that are doing this kind of analysis, right? Doing this kind of like, hey, it turns out if you do blah, 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 it all works out, right? So like, I can't wait to see like some kind of AI discover in some weird, obtuse way how to basically 10x the amount of throughput. And maybe we do end up in a world where your crusty old 3090 GPU on your personal computer can run a like big model with a ton of LoRa's in a relatively small amount of time, because we've figured out some magical fused kernel that like does everything at the same time. I don't know. A man can dream, right? Okay, so that's basically the paper. The next section here is the evaluation. They're basically going to evaluate this on a bunch of different Llama models with different LoRa's. So here they have Llama 7B, which is the small one, and then you have Llama 30B, Llama 70B. This is giving you numbers for the adapter, so that's that R, right? Adapter rank R. So you can see how for the small models you have an adapter rank of 8, which is still much smaller than this 40,000 or 4,000 hidden size. And it seems like for some of the bigger models, they choose to go for bigger adapter ranks here. So here you have a 8,000 hidden size and a 64 size for the rank of the LoRa's, but 64 is still definitely smaller than 8,192. They try this on a couple different GPUs here. They try this on a NVIDIA A10 with 24 gigs, on an A100 with 40 gigs. They try it on the fancier A100. There's A100s that have 40, and then there's these big boy A100s that have 80. Host maze memory ranging from 64 gigabytes, which is kind of what you would expect at a home setup, and then 670 gigabytes, which I don't think any of you probably have that at home, but we will show that S-LoRA can efficiently scale, limited only by the available memory. They benchmark to a couple different variants of S-LoRA, so they're going to be comparing to Hugging Face PEFT, library for training and running parameter efficient fine-tuning models, LaX advanced batching and memory management. And then they're also going to compare to the VLLM, which is the original paper, this one here, the VLLM system overview from this efficient memory management for large with paged attention. Simple multi-model serving based on a high throughput serving system. Does not support LoRa. We merge the LoRa weights into the base model and serve the multiple versions of the weights separately. To serve M-LoRa adapters, we run VLLM workers on a single GPU where multiple workers are separate processes managed by NVIDIA MPS. The fuck? I didn't realize you could do that. Damn. You can do that? Holy shit. You can literally run multiple workers on a single GPU. NVIDIA has their own kind of threading type of thing. It's fucking crazy. S-LoRA, no unified mem, so without the unified pool. S-LoRA using a first come first serve, so without the extra crap where it tries to batch it based on whether or not they're using the same LoRa. And then S-LoRA BMM, which is without unified paging and customized kernels. Copies the adapter weights and performs batch matrix multiply with padding. Okay, so this is the worst case. So this is going to be the shittiest one, and then we'll see. Let's see. Throughput requirement comparison. Default parameters. Okay, so they have synthetic workloads, so they're basically just pretending that there's a bunch of users coming in with different requests to use different LoRas and different prompts, which are going to have different numbers of tokens, right? The sequence length is going to matter, which is going to change the KV cache per user, which is going to make this a little bit more interesting. Given an adapter's gamma arrival process. Okay, so fancy distribution for the really, when you're running this, you're going to run this in the real world, and in the real world, there's some distributor, people are going to log on to their computers more in the morning or in the afternoon, so you're going to have a different type or distribution of requests in the real world. Here, they're kind of trying to synthetically create that. They're trying to say, okay, well, you're going to have some kind of power law distribution of people requesting shit at different time, but I don't know if that's necessarily good, right? I bet you that whatever they came up with here is not going to be necessarily super representative of an actual workload. I would have almost liked to see this more with a real workload, right? They should have recorded a workload from a real system and then just played that. But, this paper's pretty cool, so I'll cut them some slack. The throughput and average latency request for an S-LoRa and its variants. S-LoRa achieves significantly better performance and can scale to a large number of adapters. Okay, so what do we got? S-LoRa, S-LoRa BMM, and S-LoRa no unified memory. This is the 3 different ablations that they did here. So obviously S-LoRa is the fastest, has the highest throughput pretty much every single time, and has the lowest latency. So the blue line is at the bottom every single time here, and at the highest. Oh, interesting here. It's not here. So right here, if you have only a few adapters, if you have less than 100 adapters, or less than 50 adapters, so less than 50 LoRa's, you have faster latency without the unified. Okay, that makes sense. It's if you don't have that many LoRa's, you might as well just load them as is. But overall, I feel like this obviously works. Obviously this is trying to show you that the blue is by far the best. S-LoRa can serve up to 2,000 adapters simultaneously. That's fucking crazy. 2,000 different LoRa's, right? How many different LoRa's could you have for a language model? Seems like a lot. VLLM pack needs to maintain multiple weight copies and can only serve fewer than 5. The throughput of VLLM pack is also much lower due to the missed batching opportunity. Although PEFT can swap adapters, enabling it to handle a large number of adapters, it lacks advanced batching methods. S-LoRa achieves a 4x higher than VLLM packed, and then 30x higher than PEFT. So those are impressive numbers for sure. Okay, I'm going to compare it to some other stuff. I'm just trying to speed up here because I see that we have 10 minutes left here. So end-to-end results. Oh, okay, damn, all right. So there you go. They did do it on real workloads. I thought they were just going to do this with synthetic, but I guess they did record. So they basically had some chatbot arena, and then they basically, I guess, probably recorded what a bunch of users requested for a bunch of time. Yeah, the raw log can be sampled into traces, then they basically fed it into their thing, and then how much does it do? Does it do well? Figure 7 shows the throughput, and we still have the blue line is the best. Perfect, nice. Okay, so with fake workloads, it's the best, and then with real workloads, it's also the best, so you love to see it. We test the scalability of our tensor parallelism by running it on... Okay, so this was just one GPU systems. Now they have multi-GPU systems, so they have a Llama 30B that is split into 2 A100s and 4 A100s, and then a Llama 70B that's split on 2 A100s and 4 A100s with 10 adapters. Okay, what do we get from that? Still the best. Blue is the best. Pretty good. Merging adapter weights, computing on the fly. Early abort. Oh yeah, they did some fancies. Okay, whatever. I'm not even going to go into that. Fancy related work. Conclusion. We present S-LoRA, a system capable of serving thousands of LoRa adapters from a single machine with much higher throughput compared to existing systems. S-LoRA is made possible by our innovative design of the unified memory pool, tensor parallelism strategy, adapter batching, and CUDA kernels. S-LoRA enables large-scale, customized fine-tuning services essential for deploying models tailored to diverse requirements. Future extensions of S-LoRA will encompass support for additional adapter methods, enhanced fused kernels, and the use of multiple CUDA streams to parallelize base models and LoRa computations. This is work that has been supported by, a ton of different works here. We got Google, IBM, Intel, Microsoft, and then some Saudi oil money as well. Samsung, Uber, VMware, all right. There's a lot of people putting in money. And what do we got here? Anything interesting? Adapters, proofs. Okay. Pretty cool. Let me take a sip of this water and you guys ask any questions and then we'll summarize what's going on. Okay. All right. So today we reviewed a couple different LoRa papers. So we reviewed LCM Lora, S-LoRA, and then LoRAX. So all of these papers are slightly different, but we went through all of them. So the first paper we went through is called LCM Lora, and this is a kind of a cool little paper from some people from Hugging Face and Tsinghua University, where basically they take the latent consistency models or consistency models applied to latent diffusion models, and these are basically a model that distill diffusion models such that they can work with fewer amount of steps. So basically, rather than working with 10 steps, they work with 4 steps. But the clever thing that they do is rather than using it to distill a new latent diffusion model, they basically do this consistency model, but only into a LoRa. So they basically take all that consistency model benefit and put it inside the weights of a LoRa so that you can then add it to your already existing diffusion model. And what that does is it basically allows you to do diffusion models that now work in less steps, right, as you can be seen here. And because it's now a little LoRa, that means you can combine it with other LoRas, right? So you can combine it with a LoRa that you have for a specific style. So you can combine this LoRa, which basically just makes your diffusion model faster by having it work in fewer steps, with a LoRa that has a specific style. And what that results in is basically kind of this demo, which I highly recommend people try, a Toad on a car. How about that? It's super fast. It's super kind of cool and clever. But yeah, very nice little cool paper. The next paper we looked at, it's not really a paper. It's called X-LoRA. It's basically, I don't even know why we mentioned this one. Maybe just because it had the word LoRa in the name. But basically it's this idea of like, can we be efficient about how we load LoRas such that when we have a bunch of users that want to request different versions of models, right, different models that have been fine-tuned on different things with different LoRas, like I want to be able to serve all of them with just one compute node rather than 10 different computers with 10 different LoRas loaded. That's much more inefficient in terms of like money that I'm paying for inference, right? As a server of user requests, I want to be able to serve in the least amount of computers possible so that I don't have to pay a huge AWS bill at the end of the day. I don't want to have that French poetry LoRa model just sitting there in the cloud, just racking up my cloud cost if there's only one user request every hour for that model, right? So then we get to the final paper that we reviewed, which I think is the coolest paper, and this is a very awesome little paper. I guess it's not even little, it's a big paper, but this paper is called S-LoRA, 7th November 2023, serving thousands of concurrent LoRa adapters. And basically what they do in this paper is there's two kind of key things that they realize. So the first thing that they realize is that LoRa adapters have a dimension of R by H, where R is the rank of the LoRa adapter, right? So the rank, which is something like 8, and H is the hidden dimension. And it turns out that that H is also one of the dimensions of the KV cache. The KV cache is basically your encoded information. So the part that you encode whenever you're doing this encoder-decoder transformer, right? You're encoding your prompt into these KV matrices, which are then used for cross-attention with the decoder at every single token, right? So your encoder is here, this yellow, and then your decoder is this purple stuff. And you're caching that KV so that you don't have to constantly keep calculating it every time. And they figured out that, hey, wait a second, the LoRa and the KV cache can be cached in the same unified memory pool because they share that one dimension. Pretty clever. Okay, the other important thing that they realized is that, hey, rather than merging in the LoRas, which is what most people do, most people will train their LoRa and then they'll merge it into the base model and then serve that base model. But in this paper, they were like, keep that separate. We keep the LoRa computations separate from the base model computations so that we can batch user requests much more efficiently. So now all we have to do is do the batched base computation for the base model, and then we do all of our little LoRa computations here on the side, and then we basically add them into the original base model at the very end, right? And part of the reason why this works faster is because the communication overhead of communicating the intermediate results of these LoRa computations is actually much smaller than the total time it takes to actually do the base model computation. So you can do a little bit of communication while the other GPU is working on the base model, and then in that way, you basically end up getting a faster system overall. And very clever solution, very clever kind of system, and it also kind of does pretty cool stuff with in terms of managing the memory on that unified memory pool, in terms of like, okay, you have different user requests. The user requests have a certain time that they need to be served in, and so on. I think I'm already out of time, but I'm going to keep it going a little bit longer here on YouTube. Maybe answer a question. Is S-LoRA single QK through many LoRas? S-LoRA is many user requests, so there's going to be different KV caches depending on the user request. Can we use S-LoRA in a stable diffusion model? Probably. It's not implemented, so you're going to have to do a bunch of things yourself, but you could definitely do it. Wouldn't each GPU working on base model all gather if it's blocked by slowpokes? Yes, there's probably going to be situations where this doesn't work well, right? Like depending on where you're putting your LoRas, right? The LoRas they're not all in the same place, so different models might have different LoRas in different places, and if you put them in different places, it might just work out such that this is actually terrible. So for your particular hardware setup, for your particular model, for some specific type of distribution of user requests, you're going to have different ways of making this optimal, but I think this general idea should probably help. Cool. That's basically it, guys. Hope you guys found that interesting. Tune in next week for more streams. Thanks, Liu, Jim, Generalist, Josh, Khalil, Din, Emily, Ed, who else? Albog, Khalil, the Yivian, the High, Josh, everyone else. Thanks for that. Hope you guys had a cool stream, and see you guys later.